So now we'll pick up on our journey of extending Newton's laws of motion to complicated systems. We've already taken a look at systems that are rotating, and now we want to take a look at fluid systems. So to this end, I first have to define a couple of terms. I'll start by defining the term fluid, and that is anything that under the influence of an external force can flow to assume the shape of a container. So for instance, this could include things like, say, any liquid, gas, or plasma, but it could also include some things that you might find a little surprising. For instance, silly putty counts as a fluid. You can mold silly putty into some little shape, then you can stick it back into its little egg. And if you come back about a year later, you'll find that the egg, that the silly putty has flowed down to match the shape of the egg. So that counts as a fluid. It's just a very, very slow flowing fluid, but it counts as a fluid. The Earth's asthenosphere, just right underneath the crust, would be another example of a very, very slow moving fluid, but it would count as a fluid in this definition as well. What would not count as a fluid in this definition is glass. A lot of people have it in their mind that glass is an example of an extremely slow moving fluid, and they usually point as an example to the construction to homes of construction of more than a century old. You go and look at some old farmhouse, you had those really tiny little panes of glass all strung together, and people look at them and point out that the fat end of the pane of glass isn't a uniform thickness anymore, and that the fat ends are all at the bottom. Turns out that a glass is its own special kind of state of matter. It distinguishes from a normal solid in that a normal solid will have what's called long-range order, where a bit of material far away will look just like a bit of material nearby. Glasses have what are called intermediate range order, which is that neighboring bits tend to look like each other on a molecular scale, but as you get further out, how they look changes a bit. But it isn't a fluid. It doesn't flow. So why do you see that with the farmhouses? Turns out the explanation is much more mundane. We haven't gotten good at making glass of uniform thickness until comparatively recently in history. And so when you would be making the glass for, say, some old, when that old farmhouse was built, the panes of glass were not of uniform thickness, just plain because they were made that way. And then when you go and stick the panes of glass into the window, because it feels more stable, the thicker ends would go to the bottom, right? That's more stable. You have a wider base of support. And so just instinctively, the builders tend to put the fat ends of the panes of glass to the bottom and which will leave the skinnier ends more toward the top. So it isn't actually flowing. A piece of glass that was made, a couple thousand years ago will look the same then as it does now. But water, on the other hand, is a good example of a fluid. If you pour it into a glass, it looks like the glass. Okay. Now, it turns out that modeling fluids in general is an insanely difficult thing, having to do with issues of the molecular forces and stuff like that. A lot of them can be very hard to model. But it turns out that there are a lot of situations where we can idealize the situation, look at what we call an ideal fluid. In an ideal fluid, what I'm envisioning for now, and we'll have to extend this definition, is a bag of weakly interacting molecules whose volume cannot change but shape can. So what I'm imagining is like if you have like a Ziploc baggie full of BBs or something like that. The BBs are free to slide around past each other, but it'll always have the volume of the Ziploc bag no matter how you squish the bag. So that's the sort of the mental picture that I'll have for now. When we start worrying about fluid flow, we'll have to stick another couple of terms and conditions onto this. And it turns out that there are plenty of situations. For instance, a gas in a sealed container isn't too bad here. It will assume the shape of its container. Interactions between the molecules are very rare. So as long as you don't give it a mechanism for the volume to change, you're good to go. So there are examples of ideal fluids. And then there are fluids that are ideal enough. Water is not incompressible, but it takes an awful lot to compress it just a tiny little bit. So for a lot of stuff, when we look at water, we can approximate it pretty well as an ideal fluid. Now, as a bit of a further segue into looking at fluids, we need to also remind ourselves of the definition of density. And this is something that you're likely to have seen in another course in some previous lifetime. But again, a little bit of care is worthwhile here. First off is a notational issue. The symbol for density is the lowercase Greek letter rho. So if we use the special paper that we learned to write with, it would look something like that. Yeah, okay. Third tries the charm, there we go. And whatever you do, resist the urge to turn it into a tadpole. All right. So it's not a P. And this is important because density and pressure will show up a lot in the same equations. So you'll want to be careful to distinctly draw your rhos apart from your P's. A totally acceptable alternate way to draw the letter rho, if you're having a hard time doing that, is like that with a little hooky on the end like that. That's also a very common way to write it. Okay. Either way, the density of a material is defined to be the ratio of its mass to its volume. So again, here you need to be a little bit careful because for a physicist, the natural choice of units for density, if we're working in SI, is going to be kilograms per cubic meter. If you've had prior exposure to this in chemistry, say, chemists quite understandably use grams per cubic centimeter because they tend to work in quantities of about those sizes. Now the thing is that if you follow through all the unit conversions, what you'll find is that if you just have the numbers committed to memory for certain substances without the units, you can find yourself off by a factor of 1,000. So for instance, to a physicist, when we write the density of water, so the density of water would be 1,000 kilograms per cubic meter. I mean, that is equal to 1 gram per cubic centimeter, but because everything else is in meters and kilograms and stuff like that, a physicist is going to prefer these units, and so all of the numbers are a factor of 1,000 bigger than what you might be used to from, say, chemistry or biology or fields like that. Okay, similarly, as we get into defining pressure, we're going to find that the units that physicists prefer will be very, very small compared to other units that are widely used. So let's go and define pressure here. So here the notation I'm using is a capital P. And I'll try to remember to put a little bar at the bottom, at the base of the P, just to help make it extra distinct from rho. And the pressure that something feels, let's think about how a pressure gauge actually works. A typical pressure gauge is going to be some sort of a contraption. You know, this is a perfectly good example where you have some sort of a little piston, and as the gas molecules strike against the piston, they'll exert a force on the piston, which you can measure with a little spring. And then you have a known area here. And it turns out that the pressure that you will experience, it will be the ratio of the force applied to the piston to its area. So if I double the area, the piston will be feeling double the force. It'll also turn out that if you're in a fluid, it doesn't matter which way you point the device. So we can write pressure as a scalar even though force is a vector. So again, for the units here, the natural choice of units for pressure is going to be the Pascal. Symbol for Pascal, capital P, small a. That will be 1 Newton per square meter. And again, this is the natural choice just because all of our distances are in meters and all of our forces are in newtons. However, 1 Newton isn't an awful lot of force, and 1 meter is an awful lot of area. So for reference, atmospheric pressure, that's sea level, sure I can spell, atmospheric pressure is 101,300 pascals. So that's a lot. So it often gets written as kilopascals. So move the decimal point 3 to the left, 101.3 kPa. And in fact, a mnemonic that I have for remembering what atmospheric pressure is if you live on the west of the Mississippi in the United States, radio stations all begin with the letter K. So we could imagine the ident for the hourly ident for some West Coast radio station would probably go something like this: 101.3 kPa. Seriously, just sing that along a few times and you'll never forget it. You may want to, but you'll never forget it. So it's a handy way to remember it. Okay, so why do we feel all that pressure? And we'll get back to the other units of pressure in a bit. But first I just want to segue for just a quick moment and say, well, why do we feel all that pressure to begin with? And now here the answer is it's going to depend. So we'll say causes of pressure here. It's going to depend on what kind of a fluid you're looking at. If you're talking a liquid, so let's say I have a liquid in a box. There we go. So as I descend down the liquid, like so, any point here is going to be feeling the force is going to be feeling all the weight of the liquid above it. All this liquid is going to be feeling force of gravity. And this liquid here has to push up on the liquid above it to keep it from passing through. Ditto the liquid beneath it. This whole stack of liquid here is feeling force of gravity trying to fall down. This liquid's having to push up. So you can see as you go further down, the stack of liquid that you worry about keeps getting bigger. That means the force of gravity on that liquid on the stack of liquid will keep getting greater, which means that the liquid underneath has to exert ever greater forces. So as we descend, the forces that chunks of liquid have to apply to each other increases. And so this means that the pressure will increase as you descend due to the weight of the so pressure will increase as we descend due to the weight of all of the liquid above it. For a gas, with the caveat that the box is a reasonable size, like say a room or something like that. Here what's going on is the gas molecules are just free to fly around in any old which direction they like at any old random speed. And we will eventually get that all tied together in future videos. But what winds up happening is that the walls are going to be feeling a pressure just plain due to the collision of the gas molecules with the wall. That will exert an impulse, and so you'll feel pressure. Now the thing is the density of the gas is much, much lower than the density of the liquid. So although there is also the issue that as you descend down in the gas, you have more gas above than below, and so you'll have to support it, and so the pressure will increase. That is very weak in comparison. Now the exception here is if my container is, say, planet-sized or something like that, then the effect that predominates in liquids will also start to show up in gases as well. But for a reasonable sized container, the main thing you have to worry about is the thermal motion of the molecules. But I did say if the room is really, really big, so now we can take a look at atmospheric pressure a little more. Let's say you're standing here on the surface of the Earth. You'll have literally all the air above you. It will be feeling a force of gravity down. And if you weren't pushing up on it to support it, it would fall right through you. Now, thankfully, it isn't just you. It's also all the air that's around you is also helping to push up. Otherwise, you would be totally glued down and you wouldn't be able to move at all. So be glad for that air underneath helping you out. But as you descend in altitude, this box of all the air above you, as you descend, will get bigger and bigger and bigger. Or flip it around, if you go up a mountain, the box of all the air above you gets smaller and smaller, so the force of gravity gets less and less. So therefore the force required to keep it from falling through you decreases as well. So pressure will decrease with altitude. Now, unfortunately, there's only a few zillion different units used for pressure. So let's go and work through a few of them. So a common one that you'll see in a lot of applications is the atmosphere. And we've already seen that that is 101,300 pascals, or 101.3 kilopascals. Now, if you take a look, an atmosphere is just a little over 100 kilopascals. So here's a good time to pull out the old hecto prefix. Remember, hecto means times 100, where kilo means times 1,000. So you can write this as 101,013 hectopascals. And you can say that 1,000 hectopascals is a bar. So this would be 1.013 bar, or 1013 millibar. And a lot of the world uses either millibar or kilopascals or hectopascals. It fluctuates by country, what they deem convenient. Another common unit is, it turns out that the weight of all the air above you is also equal to the weight of a column of mercury that is 760 millimeters high. So you may have run into the unit millimeters of mercury, which the millimeter mercury also gets called the torr, in honor of Torricelli, the person who created the first barometer and ran up and down mountains to help finally put to rest the age-old conundrum that had caused the ancient Greeks to reject the heliocentric model of the universe, even though they knew that that would make more sense than the geocentric model. You see, they realized that with the heliocentric model, in order to have the sun rise and set, the Earth would have to rotate. However, they knew roughly how big the Earth was, and so they could work out how fast something on the surface of the Earth would be moving through the air. They then realized that these winds would make a hurricane seem like a gentle breeze, and since everything hadn't been completely leveled by the winds, they had to reject this better model in light of observational data, and they wound up going with the geocentric model, which would allow for the Earth to not rotate. However, it turned out that the resolution to the issue was that which Torricelli was able to demonstrate, is that for all practical purposes, the Earth doesn't have an atmosphere. Now you might say, hey, wait a minute, I'm breathing one right now. I'm pretty sure the Earth has an atmosphere. Yeah, but as planets go, it isn't much of one. If you were to take the Earth and shrink it down to the size of an orange, what Torricelli was able to show is that the main part of the Earth's atmosphere at that scale would be the thickness of the orange part of the orange, not the nasty white stuff underneath the orange peel, just the orange peel itself. And so the Earth's atmosphere is so thin that it's easy for the Earth to drag it along with it in its rotation. And so for the most part, the Earth's atmosphere rotates with the Earth, and thus we do not have the oppressive winds that the ancient Greeks were concerned about. Okay, so with this one, we've introduced pressure. In the next video, we'll go ahead and extend this to develop fluid statics.